Okay, folks, we're starting soon. Let's let's get it all together and see what goes on today. Welcome to my stream. This is Vintage, and we are going to do math today on the most technologically advanced thing from probably 3000 BC, paper. Paper, guys. All right. Yeah, so today I'm going to be working on math synopses of classes. So we're going to do geometry, algebra 1, algebra 2, pre-cal, and calculus, or maybe just algebra 1 and calculus, depending on how things go. I think what I'm going to do is, well, let's see, what books do I have around me right now? Oh, I know. I'm gonna don't tell anybody this. I'm gonna lift the list of topics from each course from Khan Academy. Sorry, guys. I mean, from a very old Algebra 1, Algebra 2, Algebra Pre-Cal, and Calculus textbook. Right. Let's see. All right. So, let's get started with geometry first. That's the one that I've kind of thought the most about. So geometry, there's a few things that geometry starts out with. It starts out with angles and points and segments and lines and rays. So, so it starts out with these very, very, very basic, I was gonna say shapes, but not shapes. Basic structures, I guess. And that's where the structures start out. The logic starts out with postulates, which are basically statements that we agree to be true. Hold on a second. Statements agreed to be true. So if we're building a geometric house, we start with the postulates, and then we get to theorems. And after that, more complicated theorems. So that's kind of the way it works. Well, how would you put that nicely, though? Okay, so so that's the logic. The logic starts with postulates and then levels of theorems. I think that's a good way to put it. Floors of theorems. So postulates would be like the ground, and theorems would be floors in a house or building. Okay. So yeah. And that's the logic side of it. The structure side of it is you start with your basic structures. And then you go to Angles, points, segments, rays. Yeah. Start with the basic structures, and then you prove stuff, a lot of stuff about triangles and parallel lines. Oh, actually, that's technically. Let's put that here. Triangles, and then in general, polygons. And separately, I guess, you have like a circles track. So yeah, that's the logic there. So I think we've covered almost everything that we do in that class as far as 2D stuff. There's some added content with constructions. Okay, I can't read that either. Sorry, guys. And yeah, I want to say this is pretty much. Oh, hold on. Yeah, I want to say this is pretty much the roadmap for geometry. I'm probably missing some things here, but I'll go back and check a geometry book to make sure. But yeah, postulates, and then sort of levels of theorems, and parallel lines with your basic structures. Actually, maybe I should put parallel lines second. So yeah, this will be second. Basic structures, angles, points, segments, rays. A little bit about parallel lines, and then we go to triangles-ish. And then we go to polygons. And then there's a little offshoot for circles, for the chords, theorems, and tangent theorems and stuff like that. But yeah. Yeah, triangles takes a long time to get through. You have your isosceles triangles, you have your equilateral triangles, you have right triangles, obtuse, acute, and some combinations of those sometimes. And so that's kind of the way that is. Okay, let's do calculus, because that's the sort of very easy one. Calculus. I'm talking about calculus AB here. So calculus AB has some pretty simple stuff. Let me think. Yeah, it's just limits and derivatives and integrals, and then applications of the three. So limits, derivatives, integrals. All right. Limits allows us to deal with closeness / infinitesimals. Derivatives help us deal with rates of change. And integrals help us deal with area. Or this is slope. Let's try, yeah, let's just put area for integrals. And summations. Limits of summations maybe is probably better. And slope should be instantaneous slope. Okay. And then we have limits is oh, what do you call it? Oh, applications. And derivatives of applications. And integrals of applications. All right. So application of limits include asymptotes, continuity. Let's see what else. Limits, asymptotes, continuity. I want to put underneath this. Well, so this would be like a web. Asymptotes have to do with end behavior. And, what do you call it? I'm not thinking today. That other thing, which I'll put 2 question marks for right now. Continuity, on the other hand, has to do with holes and what was the other thing? Holes, continuity. Brain just turned off. Continuity, holes, and oh, drat. Anyway, okay. So, yeah, okay. So we'll just leave it at that. Okay, applications of derivatives. We have the good old optimization problems. We have related rates. We have implicit differentiation. Integrals. We have oh, I should probably, well, okay. Let's put physics in general. Lots of physics problems with derivatives and integrals. Let's put physics back here too. Okay. And applications. Integrals. Well, this is kind of a combination of both, but well, okay, let's do area. Solids of revolution. With derivatives, we have arc length. What else is there? Something else with derivatives. Yeah. Okay. So, and then more physics. Lots more physics. Lots of derivatives and integrals in physics. Okay, let's see. And let me think if there's anything else that's in CalGAB that I'm missing. Slope fields. Which is kind of a derivatives thing, so let's just put an arrow. Okay. Alright, cool. Let's see what else is going on here. Alright. Oh, there's approximation in Calc 1. So let's add to this Newton's method and oh, what's the other thing called? Trapezoid rule. Newton's method, left, one-way trapezoid rule. Okay, cool. All right, so we got all that. All right, I think. Okay, I said I was going to do Algebra 1. Algebra 1. So, Algebra 1 starts with a review. PEMDAS. Decimals and fractions. Sometimes you study square roots before you start Algebra 1. But definitely powers. Let's see, what else is a review for Algebra 1? Sometimes there's a little bit of Cartesian coordinate stuff. But not a lot. Well, that's not true. Well, let's just put that in. Okay. Let's see, what else? All right. Okay, so we learned properties of real numbers. We learn properties of real numbers. Okay, so that seems okay. And then we learn linear equations. Not like systems of linear equations, which is what linear algebra is about, but like actual linear equations. So 3x plus 9 equals, I don't know, 5x minus 3. And solve. And just for fun, plus, oh dear, I want it to be a minus, so I'm going to write this backwards. Let's make this a 4. Okay. Oh, well, that's not good. Let's make this a 3. Okay, that'll give an integer answer, I believe, for x. Not that we have to have an integer answer, but just for the example, it's nice to have one. So that's the first part, and I like to teach the chocolate method here. I can't spell chocolate. Chocolate method here, and then yeah, good stuff. Chocolate, we'll call it the chocolate box method, I think. Box is probably important in that name. Yeah, let's just go through that quickly. It's kind of a cool method. It teaches all the basics of solving almost every linear equation. So I like to put it in my own method of teaching Algebra 1 because it's a logical way of thinking about variables in general, especially for linear equations. So here's the game. Here's the chocolate game. You have a friend, and you're both in class, and the teacher gives you a box of chocolates. Doesn't tell you how many chocolates are in it, but gives you a box of chocolates. The teacher then gives your friend on the other side of the page or room 4 chocolates, and the question is, if you two have the same number of chocolates, how many chocolates are in the box? This is basically, actually, let's do this. Hopefully I won't run out of room. But this is basically x equals 4. What is x? So that's kind of obvious. You just like, okay, there's a box, and that's 4. And so the first round is done because the box has 4 chocolates. Okay, so the next problem is slightly more difficult. You have a box with 3 chocolates on this side, and then you have some like random number of chocolates on this side. Let's make it 8, let's say. And you're asked to figure out how many chocolates are in a box if the 2 sides are the same. So this is equivalent to this. And what we do is subtract it from both sides in general. But if you think about it with the chocolates, yeah, you can just guess to see how many chocolates are in the box, but one of the one of the logical ways to go about this, another logical way to be more specific, is to cancel stuff on both sides. Like, I think if both sides have the same number of chocolates, you can easily argue with the student that if you add one chocolate to both sides, then you'll still have the same number of chocolates on both sides. But the trick here is to say you can subtract a chocolate from both sides, and you'll still have the same number of chocolates. And so, all right, so we could take away this chocolate and this chocolate. One on both sides, they will still have the same number of chocolates. Now, of course, you don't want to take away one at a time all the time. You can just take away like 5 at a time even. That would make sense, right? If they're equal on both sides, you can take 5 chocolates away from both sides, and they'll have the same number of chocolates. So let's take away 2 more together. So I'm going to take 2 away on this side and 2 away on this side. And guess what? We get one box has 5 chocolates. So that's the logic behind that. So basically the moral of the story here is, at least for the second example, that you can add or subtract as many chocolates as you want from both sides. That's the crux. So we go to the next problem. The next problem finds us with this kind of thing. So we have 2 boxes and 4 chocolates on one side. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 chocolates on the other side. And the question is, if both sides have the same number of chocolates, how many chocolates are in a box if the 2 boxes have the same number of chocolates? Okay, so that's the stipulation. And in this one, we decide that we can take 4 away from both sides, 4 chocolates, not 4 boxes, 4 chocolates. I'll take the first 2 out and the last 2 out just to be creative here. And now we have 2 boxes of 6 chocolates. Well, anybody can probably tell you that's in algebra, that by now they have the logic to say if 2 boxes of the same number of chocolates have 6 chocolates in them total, each box has 3. And the moral of that story is you can multiply and divide whatever you want on both sides of an equality of an equation, except 0, and still have a true statement. So we're going to divide by 2, and we end up with a box. And we end up with a box has 3 chocolates. Okay, so the final one before we get to parentheses, which is a whole new thing, is this. I have, let's say, 1, 2, 3, 4 boxes on this side. Let's say we have 2 chocolates. On the other side, we have 2 boxes. And 10 chocolates. And the question is, if all the boxes on both sides have the same number of chocolates, and both sides have the same number of chocolates each, how many chocolates are equivalent to 1 box? Again, this is 4x plus 2 equals 2x, 2x plus 10. And here we can generalize and say, well, we said we could take as many chocolates as we wanted out of from both sides, and all the boxes are the same, so can we take 1 box away from both sides? And the answer is yes, because all the boxes are the same. We're basically taking the same number of chocolates from both sides. Again, you can take as many boxes as you want from both sides, as long as you take the same amount. So in a way, we could just take 2 immediately and not have to worry about the 1 box and then another box. Hey, guess what? We have some chocolates here. We can get rid of this one, and sure, why not? The middle 2 here. And we find out that we have 2 boxes is equivalent to 8 chocolates, so each box has 4 by dividing by 2. And there you go. Okay, so a kind of interesting thing to note here is gift baskets for linear equations only. Gift baskets. So let's say we have a gift basket, and the gift basket has a box and 3 chocolates, and I have 4 of these gift baskets. There's no equation, there's no equality, there's just an expression. If I have 4 of these gift baskets, how many boxes do I have and how many chocolates? Well, this is the same thing as saying 4 times x plus 3. What do you get when you expand the expression? And this one, It's pretty easy to tell. You get 4 boxes. And 12 candies. On this side, we also get 4x plus 12. But this is a nice sort of logical way to think about it. Again, if you have 4 of these things, another way to look at them is you have 1 of these things, and then another of these things, and then another of these things, and then another of these things. So, this is one way to break down 4 times x plus 3. So, yeah. So again, 4 boxes, and then a bunch of chocolates. Okay, and again, over on the side, 4x plus 12. You can even use this in the equation stuff. Let's say we have gift basket here. We're just going to use this again. Why not? Because why not? So we have 4 gift baskets here. We have 3 gift baskets here. And the question is, if I can... Oops, I need more. And the question is, how many chocolates are in a box? Assuming these both sides are equal. So this is 4 boxes, and just for not drawing all the chocolates, let's put 12 chocolates here. And then this side is 3 boxes plus 15, I want to say, chocolates here. Oops, maybe we should just draw the boxes anyway. All right. We cancel chocolates, cancel boxes, so this all goes away. This becomes a 3, and we find out that 1 box actually has 3 chocolates, and there you go. So, a wildly, I want to say simplified, but it's actually just, it's a physical way of thinking about whole number variables and equations and expressions of them. So yeah. Yeah. All right. So that's going to be part of it. I'm always trying to find out if there's something extra that I'm putting in that I don't like doesn't make things more clear. I like succinct things. It makes for I think it makes for a better book. But maybe we should just go with the old teacher rule that you should repeat everything 3 times. Hopefully not, but you know, there are different families of teaching methods. Anyway, okay, so that's algebra. That's the first part of algebra. The next part of algebra is about multiplying stuff out and factoring. Factoring is a whole difficult deal. So the first thing you want to do is teach multiplication, which is, tough as it is. So we have x squared plus x plus 1. And let's say we want to multiply that by x squared plus 3x plus 4. Doesn't really matter if they're factorable or not. We're just multiplying these things out. And so the first thing you want to say is that multiplication is actually just area when you have length and width. So let's say this is the length, this is the width. To find the area, you multiply that length and width. To find the product here, you multiply the top and the bottom. The length has 3 parts added together, which I am not going to draw to scale because I don't know what x is. But yeah, so this is x squared, this is x, and this is 1. Okay? The other side of this, did I say square? I meant rectangle, sorry. The other side of the rectangle has 3 parts too, x squared, 3x, and 4. And if you look at the way this is divided up, it forms a 3 by 3. By the way, thank you guys for watching on July 4th. Just saying, you must be very diligent, or perhaps you're not from the US, but whatever, doesn't matter. Okay, so anyway. But yeah, you end up with a 3 by 3. Turns out that the areas of the small parts, the small rectangles, equals the area of the big rectangle. So all we have to do is figure out what the areas of the small rectangles are. X squared times x squared is x to the 4th. There's a little bit of exponential and variable interplay that you have to know that x squared times x squared is x to the 4th. But okay, here's x to the 3rd, here's x squared, this is 3x to the 3rd, if I can do math. This one is 3x squared. This is 3x. This is 4x squared, 4x, and 4. All right, cool. Hopefully that was all right. And then you just add up all the little areas and combine like terms. So that should be fine. X to the fourth plus 4x cubed plus 8x squared plus 7x plus 4. Hopefully I didn't get that wrong. Let's see. 7 is right. Okay. 4 is correct. 4, 3, 1. Yeah, 8. Okay, cool. So here's my answer. Not too bad, really. You have the area method, and then that simplifies to the chart method, which is listing the monomials. And putting the areas in the proper cells in the chart. So that's that. Okay. So got that. I got factoring. Ooh, fun stuff. All right. Let's see. Okay. So yeah. Properties of real numbers. Linear equations. Chocolate method. What else is there? Polynomials and quadratics. And then factoring. What am I doing here? Factoring and quadratic formula. All right. Oh man, I should really swap these. Plus, minus, times, divide. Okay. All right, and then there's graphing. There's graphing. Okay. Oops. If I remember correctly, when I did Algebra 1, we did rational and radical functions, so let's put that in there too. Okay, anyway. Graphing lines. Quadratics. Lines, quadratics. What else is there? Underneath lines, there's slope and y-intercept, slope and intercepts. Quadratics, roots, intercepts. There's some symmetry involved. I don't know if we talked a lot about it. What else is there? Oh, vertex. And, yeah. Okay. All right. Okay. Um, yeah. I'm trying to think of like tricky problems in this realm, but I don't think I can think of one right now. Like I know of some, but I think they're too complicated. I'm trying to figure out if there's an easier method. Hmm. All right. Yeah. All right. You gotta stop staring at the ceiling. Just move on. Let's see. Hum. The only time when I'm trying to add 0 is when I can take part of the thing and either factor it or complete the square. I can't think of anything else right now that would be helpful. Oh, that's a nice one. Actually, I just thought of one. Okay, so yeah. Let's try x plus... Oh, well. No, that one was kind of silly too. We'll see. Well, okay. X plus 5 over 2x. Sorry, 2x plus 5 over x plus 1. So one way to do this problem, to simplify this, is to have 2x plus 2 minus 2 plus 5, added 0 there, over x plus 1. I haven't changed the top, because guess what? I added 0. So this can simplify to 2 plus 3 over x plus 1. And that might be one reason to want to add 0. Is if we represent 0 in a creative way so that, excuse me, so we can simplify the thing. But that's about it. I think it was another one. I mean, I guess you could do that with the other two, but that requires exponentials, and I don't want to mess with that. Oh wait, I know one. Factoring. X squared. Well, let's make it 3x squared, or should I? Yeah, maybe. 3x squared plus 2. And then let's put a minus 7 in the middle. X. So, one way is to pretend you're breaking up the x here. But another way is to do this. Did I mess up? Oh, I did mess up. Haha, that's not how you factor that. 3x squared. Plus 6x minus 6x. Minus 7x plus 2. Is that what I want? I think not. I think I want this. 3x squared minus 6x plus 6x minus 7x plus 2. Okay. Yeah, that's what I want. All right. So this part becomes 3x times x minus 2. This whole part becomes negative x plus 2, which is minus x minus 2. And then you can factor that. I don't know if that was really the best example of something that needs to be simplified using the addition of 0, but okay, whatever. It is an example. I guess the best example is difference of squares. Well, anyway, the other example I was thinking of was this. 2 to the 2x plus 3, when you know that x plus 1 equals 5, although you would probably just solve this and plug in 4. Okay, I don't know. I just like, or x plus 1 equals c, and you want everything in terms of c. So 2 to the c plus 1, or 2c plus 1, yeah. Okay. I don't know what I'm doing anymore. I'm just being silly. All right. I mean, there's some proofs where you start with 0, and you do good stuff after that. But I can't think of one where you're just like adding 0 in the middle. I mean, there's a lot of things in calculus where you have to do that, but I can't think of one right now. So, go me for not being able to do math. All right. What else is there? Right, so that's algebra. Okay. Yep, I am going to just probably call it a day. We got through like 8 pages of paper. So that's like probably more than 8 pages in a book. Let's see. All right, things that require. Okay. Yeah. All right. Let's do. We can do trig maybe. So this is trig, part of pre-cal. So I'm gonna like do a proof here. But I need to look up. I need to look up the identity I need to prove. Hold on, guys. Tangent. All right, the tangent half angle formula. Let's see if I can prove this using something I kind of thought up yesterday. Okay, I think it is exactly the same thing as what I came up with the other day. All right. So, let's write it out. Here's what I'm trying to prove. Tangent theta over 2 equals, let's pick sine theta over 1 plus cosine theta. It also happens to be equal to tangent of theta over secant theta plus 1, which I can use either of these because they're supposed to be the same. One is sort of fraction clearing the right one gives you the left one. So let's see if we can do this. So let's start with a thing. A thing, yeah. And let's assume for right now that theta is in the first quadrant, so that we don't end up with terrible things happen. Okay, so I have theta in the first quadrant. I have a comma b. Okay, and what I'm going to do is I'm going to put this on a circle. So this point here is on the circle with here. Basically, they're the same distance away from the origin. How do I mark this particular point? Square root of a squared plus b squared, comma 0. Okay, so if I connect these two, I form an angle. Fair enough. And what I want to do here is find the midpoint between, we'll call this O. This will be P and Q. I want to find the midpoint of PQ, which isn't too bad, hopefully. It is here. A plus square root of a squared plus b squared over 2b over 2. And that is the coordinate of the midpoint. All right, so here's where I'm going with this. Tangent of this angle, tangent of that angle is the same thing as the slope. So the slope is b over a plus square root of a squared plus b squared. The 2's cancel, and we get that. So far, anyway. Okay. All right. What have I done wrong? Hopefully nothing yet. Okay. Okay, I want to divide everything by a square root of a squared plus b squared. Okay, so I get that. So, yeah, b divided by hypotenuse is what we also call sine. And a divided by hypotenuse is what we also call cosine, and 1 is what we also call 1. So guess what? We have it right here. Okay. So that's fine and dandy, but let's try to do it a different way. Oh boy. Okay, so we get to here. That part's fine. And what I want to do is actually, no. I want to take this expression, and I believe I want to divide by a everywhere. So we get b over a over 1 plus square root of a squared plus b squared over a. Now b over a was tangent of the first thing, so that part is fine. The 1 matches the 1. And the a squared plus b squared square rooted divided by a matches the secant. And there we go. So, yeah. So the theory here is we have this segment equal in length to this segment. And we can bisect the angle by finding the midpoint between these segments and connecting the midpoint back to the origin. So this point here has this quote-unquote coordinate slash address, and we can use that to find the tangent of this smaller angle and then convert it into parts, or convert parts of it into tangents and cosines and sines of the original angle. There you go. That is the proof in a nutshell. Tangent of theta over 2 is equal to tangent theta divided by secant theta plus 1, or sine of theta over 1 plus cosine theta. And yeah, good stuff. All right. So that's all the stuff I have for today. That's not gonna speak. So that's all the stuff I have for you today. Hopefully, I'll get these together in some nice book or some nice notes. All right. Anybody watching the VOD, thanks for watching. Anybody out there or was out there, thanks for watching. I will hopefully see you next time. Take care, guys.